Welcome to the lecture on using matrices to solve systems of equations. First of all, let's define what a matrix is. A matrix is a rectangular array of numbers. Basically, it's just a way of collecting data in an organized form. And the purpose that we are going to use matrices for is to help us solve systems of equations. When we have a system, this is a 2 by 2 system right here, like this, what we're going to do first is write it as a matrix. And the way that we're going to do that is each equation becomes one row of our matrix. And when we write a matrix, we don't need to keep track of the variables, the x's and the y's. We're only going to keep track of the numerical coefficients out front. So for example, this matrix is going to have as its top row a 1, since that's the coefficient of x, a positive 2, since that's the coefficient of y, and then a 7 because that's the constant on the end. And for the second row, we get coefficient of 1, a coefficient of -1, and that -2. And a lot of times when we are working with linear systems, you'll often see these matrices drawn with a vertical line so that on the left side of the line you have your coefficients of x's and y's, and on the right side of the line you have those numbers on the right side of the equals. So it's always implied that the first column are your x coefficients, and the second column is always your y coefficients. So this matrix right here represents the original linear system that we have. Now what we're going to do with this matrix is try to do some operations on it to transform it into a special form. And the form that we want to transform it into is called reduced row echelon form, and it's going to look just like this matrix down here, where we want to have 1s along these two diagonal pieces, a 0 below, and you can have any numbers whatsoever above the diagonal and to the right of that vertical line. So we want 1s along the diagonal, 0s below, and numbers above. So this is what a 2 by 2 reduced row echelon matrix would look like. And we try to get it into this form because if we have it in this form, think about the fact that this first column is your x's and the second column is your y's. So if you look at this bottom row, translate that back into an equation. This says we have no x's and one y, or just y, and that's supposed to equal this number right here. So by putting it into this reduced row echelon form, this bottom row tells us exactly what y needs to equal. So we get one part of our solution just by looking at that bottom row. Now that only tells us y. We would still need to find x. So to find x, we're going to back up one row. We're going to translate this top row back into an equation, substitute in the value of y, and then solve for x. So that's kind of the process. Okay? So if we go and look at a larger system, we're going to be solving matrices that are starting out from a 2 by 2 system, 2 equations and 2 variables. We're also going to be solving 3 by 3 systems, which is 3 equations and 3 variables. And the reduced row echelon form for that kind of system would look like this right here, where you have 1s along the diagonal, 0s down below, and numbers up above. And this time, the first column represents x's, the second column represents y's, and the third column represents z's. So if you look at that very bottom row, there's no x's, there's no y's, but 1z equals this number. So this bottom row is telling us exactly the value for z. So that's part of your solution right there. If we back up one row, this is going to tell us how to solve for y. And if we back up to the very beginning, this is going to tell us how to solve for x. So reduced row echelon form is a very specialized form with 1s along the diagonal, 0s below, and numbers above. And by getting your matrix into this specific form, we're able to kind of solve our system a lot easier and figure out what our solutions are a lot quicker. In the most generalized case for a matrix, you might have very, very large systems like 100 equations with 100 variables. That's obviously not something we'd want to do by hand, but computers are very good at working with very large systems. In general, what a computer would do is try to get that system in that matrix into this same reduced row echelon form where you have these ones along the diagonal, zeros below, and numbers above and to the right. And that's kind of the generalized form that we want to always get to. Now, how do we get to that special form? How do we get to that reduced row echelon form? Well, there's 3 rules that we're allowed to use. And actually here, Rule 3 and Rule 4 are kind of the same rule but an extension. So you can say that we have either 3 rules or 4 rules here. I've listed it out as 4. The first rule, the first thing you're allowed to do, is you're allowed to swap any 2 rows of a matrix. So for example, if I started with a simple matrix 1, 1, 2, 2, I could swap row 1 and row 2 and get 2, 2, 1, 1. Why can we do that? Well, if you think about our initial equations up here and how they transformed into our matrix, does it matter which equation went on top? No. So it shouldn't matter which row I write first. We're still going to get the same final solution no matter which row or which equation we use on top. So that's the reason why this first rule is allowed. Okay, so we can swap any 2 rows that we want. Rule number 2, you can take any constant times a row. So for example, if I have 1, 1, 2, 2, I could multiply that top row through by -3 and get -3, -3, 2, 2, and I'll still get the same correct answer in the end. Why are we allowed to do that? Well, going back to your equations again, does it matter if I use the equation x minus y equals -2, or if I were to multiply that equation by 2 first and get positive 2x minus 2y equals -4? This would have as a bottom row 2, -2, and -4. And if I leave the top equation the same, 1, 2, 7. So from here to here, all I did was multiply this bottom row by 2. Why am I allowed to do that? Because I haven't changed the initial equation. Multiplying an equation through by 2 keeps the equation balanced, so it's still going to maintain the same solution as the original equation. So we're allowed to multiply matrices and rows by constants. Okay, rule number 3 is we're allowed to add or subtract any 2 rows together. And this is what we do when we use the elimination method when we solve systems of equations by hands. We try to get those coefficients to be the same but opposites, and then we add our 2 equations together. That's exactly what we're doing in this step. We're going to take 2 rows, like 1, 1 and 2, 2, and we're going to add them together. So 1 plus 2 is 3, 1 plus 2 is 3. And the nice thing about matrices is you actually have your choice of where you want to put that answer, those 3 3's. So if we have 3, 3 in the bottom, then we could keep the top row 1, 1 the same. Or we could put the answer 3, 3 in the top row and keep the bottom row the same. You have your choice how you want to do this, because remember, you're allowed to swap rows. So either of these 2 matrices would be correct, and they should both lead us to the same final solution. Now the last rule here is the one that's the most complicated, because here we're actually going to do 2 things at the same time. We're going to take a row times a constant and then add that result to our next row. So in this example, I am taking -2 times row 1 and then adding those answers to the second row. Now a lot of times I try not to do this in my head because I'll make lots of arithmetic mistakes. So to avoid that, what I do is I kind of show my work a little bit. If I take -2 times this top row, then 1 times -2 would be -2, and 1 times -2 would be -2. There's step 1, doing the multiplication. Now step 2 is to add that answer to the bottom row. Negative 2 plus 2 is 0, negative 2 plus 2 is 0, and I kept my original row 1 as my 1, 1. So here's my final matrix, 1, 1, 0, 0. So this is sort of a two-step process. First you multiply through by a constant and then add that answer to another row. Okay, so these 4 steps here are the things we're going to be allowed to do. Notice that everything that we're doing to rows only. We're not doing anything to columns. We're only doing them to rows, and that's because each row represents an equation. So you have to do it to the entire row to keep the equations balanced. So let's try an example. If you've never done matrices before, these can be a little bit confusing because they're so new. So it takes a couple of examples before it kind of sinks in as to what you need to do. So step number 1, when you're using matrices, is to take your 2 equations here and write it as a matrix. So we did this earlier. The top equation, just using the coefficients, would be 1, 2, then that vertical line, and then 7. The bottom equation becomes 1, negative 1, negative 2. So here's my initial matrix. Now remember, what we're trying to get it into, our goal, is to get this into reduced row echelon form, which means getting 1s along these 2 diagonals, a 0 below, and any numbers above and to the right. My rule of thumb is to try and get this first 1 in the upper left corner first. If you can get that to be a 1, then you'll always be able to get this 0 down below it. So that would be your second thing to do. And then your last thing to do is to get this final 1. So we're going to try to get the 1 in the upper left corner first using our row operations. Then we're going to get our 0, and then we're going to get our last diagonal 1. So try to get them in this order, and usually that will work best for you. So we want to get a 1 in this upper left corner. Look it over here, I already have a 1 in that upper left corner, so that's already done. So now all I need to do is get a 0 down in this bottom left corner. So how could I do that? You have a couple of options. Remember that you can always add or subtract 2 rows from each other. So one option here would be to take row 1 minus row 2 and just subtract these 2 values. So if we did that, I'm going to keep my top row the same because it has the 1 in that upper left corner that I want to have, so we don't want to ever change that. So let's keep that top row the same from this point on. And now if I subtract row 1 minus row 2, 1 minus 1 is 0, 2 minus a negative 1, remember you get a double negative there, so 2 minus negative 1 becomes 2 plus 1, or 3, and 7 minus a negative 2 becomes 7 plus 2, or 9. So by just subtracting our 2 rows, I was able to get a 0. If you didn't see to subtract, another option would be to take this top row, multiply it through by negative 1, and add that to your second row. That would be another option. And there's many, many different ways to get that 0, but those are just 2 suggestions. So we now have our 1, we have our 0, then the last thing we need to do is make this 3 turn into a 1. And you can always make that last diagonal value become a 1 by dividing. All I have to do is divide this entire second row by 3. So we're going to take row 2 divided by 3. Remember, you're allowed to multiply, which also means you're also allowed to divide any row by any constant. So if I want to make this a 1, all I have to do is divide it by 3 and it'll turn into a 1. So let's see what this new matrix turns into. We're going to keep the top row the same because it has the 1 that I want to keep. And now if I divide the entire second row by 3, 0 divided by 3 stays 0. 3 divided by 3 becomes 1. And 9 divided by 3 becomes 3. And now we have it in our reduced row echelon form because I have my two diagonal ones, and I have a 0 below, and I have numbers up above. So this is kind of the reduced form. We've gotten that far. Once we have it in reduced form, then the bottom row right here tells us one of our solutions. Remember, column 1 is your x's, column 2 is your y coefficients. So if I were to translate this back into an equation, I have no x's, but one y is supposed to equal 3. And there's half of my solution right there. Now I know what y has to be. To get x, I can back up one row, translate this row back into an equation, so 1x plus 2y equals 7. And we know that this is a positive 2 because the coefficient was a plus. Okay, so now here's my top row. All we're going to do now is substitute in the value of 3 for y. So this becomes x plus 2 times 3 equals 7, or x plus 6 equals 7. And if I subtract 6, we get x is 1. So we have our solution, 1 for x, 3 for y, and there's our answer. And remember, as a quick check, you could always plug 1 and 3 back into your two original equations, and it should make both equations true. Okay, so there's our first example. As I said earlier, if you've never done matrices before, this can sometimes be a little confusing, and it takes a few examples before it kind of sinks in. So let's try another one. Here's my system. The first thing I want to do is write it as a matrix. So we're going to create a new matrix. The top equation becomes my top row, and I'm only using the coefficients. So 4, 5, and -7. The bottom equation becomes my bottom row, so using just the coefficients, I have 1, -1, and 5. Now remember our goal. Our goal here is to get reduced row echelon form, so we want 1s along the diagonal, a 0 below, and numbers above and to the right. And we're going to try to get this 1 first, then the 0 second, and then this 1 last. So if we look at our matrix, we don't have a 1 in this upper left corner. However, we do have a 1 right here. And remember that you're allowed to swap rows. So we can swap row 1 and row 2, and that puts the 1 in the upper left corner exactly where we want it to be. And the top row becomes now the bottom row. So all I did there was swap row 1 and row 2. Now once you get a 1, you should always be able to get a 0 down below. And the way that we do that is just how we would do it if we wanted to use elimination, the elimination method. We would want these two coefficients to be the same number but opposites. So if I want to get rid of a 4, then what I can do is take -4 times row 1 and add that result to row 2. So you take whatever number you're trying to get rid of and multiply the one row by its opposite. So I'm going to take row 1 times -4, and then in the same step I'm going to add that answer to row 2. That's a lot to keep track of in your head, so a lot of times I like to write out what the multiplication part of this is, and then I will add that answer. So let's first multiply this top row by -4. So 1 times -4 is -4. -1 times -4 is +4, and -4 times 5 is -20. Now we're going to add that answer to our bottom row. Now, where do we put our answer? Well, we want to get 0, right? And -4 plus 4 is 0. Remember where we want that 0 to go. We want it to go in the bottom left corner. So you want to put your answer in the bottom row. So -4 plus 4 is 0. 4 plus 5 is 9. and negative 20 plus negative 7 is negative 27. What should we put in the top row? Well, remember we want a 1 in that upper left corner, and we had a 1 in the upper left corner if we keep this first row the same. So I want to keep the 1, minus 1, and 5 that I originally had before I did any multiplication. That way I have the 1 that I need and the 0 that I need. So we have the first column done. All we have to do to get this into our final reduced form is change this 9 into a 1. And remember that you can always make that happen by dividing. So all I have to do here is take row 2 divided by 9. We're going to leave the top row the same. And if I divide 0 by 9, it'll stay 0. So I'm not losing that 0 that we worked so hard to get. 9 divided by 9 is 1. And negative 27 divided by 9 is negative 3. So now we have our two 1s along the diagonal, we have our 0 below, so we're ready to get our answer. And you get your answer starting with the bottom row. Remember, this is x and this is y, so this bottom row tells me that y must be negative 3. So now we know y. All we have to do now is find x and we'll be done. So to get x, we're going to back up one row, translate this back into an equation. So I need 1x minus 1y equals 5. And we can now substitute in what y was equal to. So this becomes x minus negative 3 equals 5, or x plus 3 equals 5. So if I subtract 3, we get x is 2. So our final answer, 2, negative 3. Most instructors will tend to give you solutions that are always going to come out to nice even numbers, nice integers. So if you're getting fractions or getting decimals, that's probably a clue that you're doing something wrong with your arithmetic, so you'll want to double check your answer. Okay, let's try another example. Step number 1, take your system as equations and translate it into a matrix. So this is going to turn into 5, 2, 8, and 3, negative 1, 7. Now remember, our goal here is to get 1s along the diagonal, a 0 below, and numbers above and to the right. So if we look at this problem, I don't have a 1 in the upper left corner, and there's not a 1 down below, so I can't just swap these out and make that 1 just appear. This is an example where it's hard to get the 1. So you have to be a little bit creative sometimes in how you can make that happen. One of the things that I often will look for is I'll look at these two coefficients, the 5 and the 3, and somehow I need to get that to be a 1. So you want to try to think of how you could make these two coefficients possibly have a difference of 1. So right now they have a difference of 2. Is there anything that I could multiply one of my rows by so that the new number with the original number that I have up above or down below has a difference of 1? So in other words, if I have 5 here and 3 here, one thing I could possibly do is multiply 2 times row 2, and that would change this 3 into a 6, and that way 6 and 5 have a difference of 1, so I could then subtract the 2 and get the 1 that I'm looking for. Okay, that's kind of tricky to see, and that's not the only way to make this happen. You could subtract your 2 rows, and 5 minus 3 is 2, and 2 and 3 then have a difference of 1. So there's many, many ways to get a 1 here. You just need to think of one way that will work. Now you could also do this in one step. I'm going to show it to you in 2 just so that it's a little bit more clear what we're going to do. I'm going to leave the top row alone, and all I'm going to do is multiply this second row by 2. So 3 times 2 is 6, negative 1 times 2 is negative 2, 7 times 2 is 14. Now if I use these two numbers, 6 minus 5 equals 1, and that's what I'm trying to get at. So I can take row 2 minus row 1. So we're going to do 6 minus 5, and I'm going to put that answer in the upper left corner because that's where I want my 1 to go. So 6 minus 5 is 1. Negative 2 minus 2 is negative 4. And 14 minus 8 is 6. So there's that 1 that I wanted to have. Now which row should I keep down here? It's kind of your choice. You can keep the 6, negative 2, and 14. You could also keep the 5, 2, and the 8. That's kind of one of the reasons why matrices are sometimes tough, is because there's so many choices that you can make. Since I put my answer up in that top row, I'm just going to leave my second row the same as the second row that I already have. So I'm going to leave this as 6, negative 2, and 14. You could also have left it as 3, negative 1, and 7, just dividing this through by 2. So that's kind of your call. So after a little bit of work, we finally have a 1 in that upper left corner. Now that we have a 1, we should always be able to get a 0 down below. The way that you get your 0 is you take whatever number you're trying to get rid of, which in this case is 6, and you multiply your row that has the 1 by the opposite of that number. So I'm going to do negative 6 times row 1 and add that back to row 2. So this is that two-step process. So let's do the multiplication first. Negative 6 times 1 is negative 6. Negative 6 times negative 4 is positive 24. And negative 6 times 6 is negative 36. Now I'm going to add that answer to my bottom row. So keep the top row the same as it originally was with the 1, because remember, we want a 1 in that upper left corner. So I'm going to keep the top row to be 1, negative 4, 6. In the bottom row, negative 6 plus 6 is 0. 24 plus a negative 2 is 22. And negative 36 plus 14 is negative 22. So we have our 1 and we have our 0. All we have to do left here is change this 22 right here and make it a 1, and you can always do that by dividing. That very last one can always be determined by dividing through by whatever number is already there. So I am going to take row 2 and I'm going to divide by 22. So this matrix will become 1, negative 4, 6. We're not changing that top row at all. 0 divided by 22 stays 0. 22 divided by 22 is 1. And negative 22 divided by 22 is negative 1. If you're working on these problems and you're getting fractions, then your arithmetic is probably off. Almost always you're going to have problems where once you divide, it should always go in evenly into both of your numbers over here, which is the case in this problem. So we have our 2 1s along the diagonal, we have our 0 below, we are all set to get our solution. The bottom row tells us the value of y, so here y must be negative 1. And the top row, if we translate it back, is going to be x minus 4y equals 6, and we're going to want to substitute in negative 1. So let me come down here. That's going to become x minus 4 times negative 1 equals 6, or x plus 4 equals 6. So my solution is x equals 2 and y equals negative 1. So my ordered pair is 2, negative 1. Okay? Alright, the next two examples that we're going to do are still 2 by 2 systems, but these are going to be special case problems. So let me show you what happens. In this next example, if we translate this into a matrix, then that top row gives me the top row 2, negative 4, 7, and the bottom equation gives me the bottom row negative 3, 6, and 5. So what we want to do here is, again, try to get that 1 in the upper left corner, then our 0, and then our 1 in the bottom right corner. So if we look at the numbers that we are given, there's no 1 over here in either of these two positions. So I need to work with the two numbers that I have and try to get a 1 out of it. So how could I do that? Well, 2 and 3, those have a difference of 1. And actually 2 minus 3, if you were to add these two rows together, is going to give me a -1, which is pretty close to a +1. I just have the wrong signs. So that's a good place to start. Any way that you can get either a 1 or a -1 out of the two numbers you initially have, that's a good place to start. So what I'm going to do here is just take row 1 plus row 2. Remember, there's always more than one way to do this, so the way that I'm showing you isn't necessarily the only way or even the fastest way. If I add row 1 and row 2, 2 minus 3, or 2 plus a -3 is -1. -4 plus 6 is 2, and 7 plus 5 is 12. Now which row should I keep down here in the bottom? It doesn't matter. I'm just going to keep that second row in the same position that it already was, so I'm just going to keep that second row the same. Now I have a -1, I need a +1, and that's easy to fix because all I have to do is multiply -1 times row 1. You're allowed to multiply a constant through an entire row. So that's just going to change all of these signs. So -1 becomes +1, -2, -12, and we're not doing anything to that second row. It's going to stay the same. So now I have the 1 that I need. Once you get your 1, you're always going to be able to get your 0. So the way you do that is you take the opposite of the number that you are trying to eliminate. I want to get rid of -3, so I'm going to take +3 times row 1 and add that to row 2. So let's write up our little numbers to see what we would get when we do this multiplication. 3 times 1 is 3, 3 times -2 is -6, 3 times -12 is -36, and we're going to add those answers down to the second row. So keep the top row the same because it had the +1 that we worked so hard to get. And in the second row, we're going to put our answers. 3 plus -3 is 0. -6 plus 6 is 0. And -36 plus 5 is -31. So we got our 1, we got our 0. We would like to get this to be a 1, and normally we would do that by dividing, but here that can't happen. We can't divide through by 0 because that's undefined. So this is how you recognize that you get one of those special case problems. If both of these x and y coefficients turn into zeros, look and see what that implies. This, if we were to translate this back, this means we have 0 x's plus 0 y's, and that's supposed to equal -31. Well, 0 x's plus 0 y's is just 0, and 0 never equals -31. So this is a false statement. Anytime you get a false statement, that means no matter what you were to pick for x or y, there's no way we can make this become true. 0 is never going to equal -31. So if there's no solution for x's and y's, then there's no solution for the entire system. Okay, so here's what you want to look for the solution that we just got. If you see zeros in both the x and the y positions, but a non-zero in the number off to the right, then that's going to be a no solution case. And if you want to think graphically about what this means, it means these two lines are really parallel lines. If you were to graph them, they have no intersection points because they never intersect. So that's why we're getting no solution for an answer. Okay, so special case 0, 0, and a non-zero number give you no solution for a final answer. Okay, let's see the other special case that you might run across. If we take this system and we translate it, we get 9, negative 3, 6, negative 18, 6, and negative 12. And we're trying to get a 1 in the upper left corner and a 1 on that other diagonal and a 0 below. If you look at this problem, there are no 1s that we can use, and it's not totally obvious how you're going to get a 1. But if we have a 9 and we have a negative 18, it isn't too hard to get the 0. So this is one example where sometimes it's easier to get the 0 first than it is to get the 1. So let's see if we can get the 0 first in this example. The reason I can get a 0 is because if I take this 9, which is in row 1, and I multiply it by 2, that's going to give me 18. So then I can add that result to row 2, and that should cancel out my negative 18. So in other words, we're going to take 2 times this entire row. Let's figure out what that becomes. 2 times 9 is 18. 2 times negative 3 is negative 6. 2 times 6 is 12. We're going to take those little numbers and we're going to add them down. So when I write my answer, since we're getting a 0 here, since 18 plus negative 18 is 0, and we want the 0 to be in that lower left corner, let's put our answer in that bottom row. So 18 plus negative 18 is 0, negative 6 plus 6 is 0, and 12 plus negative 12 is also 0. Which row should I keep on top? It doesn't matter. I'm just going to keep the original equation or original row that I had, the 9, negative 3, and 6. Now here you want to stop. Remember that these are x's and y's, so this has that 0x and that 0y, just like the last example, but what's different is this time we have a 0 on the right side of that line as well. So if we were to translate this equation right here, we would have 0x's plus 0y's equals to 0, and 0x's plus 0y's is just 0, and 0 does equal 0, so this is a true statement. And what that means is that for every choice of x and y that you pick, we're always going to get a true statement. And so what does this mean physically? Well, if you were to graph these two equations, what this implies is that these are what we call coinciding lines. And you can probably see that from their equations. If I took this top equation and multiplied through by negative 2, we get exactly the same thing as the bottom equation. So these are really the same exact line. So what does that mean in terms of our final answer? Well, if you're looking for intersection points and these two lines are exactly the same line, then where do they intersect? They intersect in the line itself. So the kind of answer that we give here is an equation of a line, and we kind of use a fancy notation for that. We use these curly braces, then we write parentheses x comma y, colon, and then pick either equation. Doesn't matter which one you use because they're both the same. I'll use the top one. Close this off with curly braces, and that is how you write your solution. So every point, x comma y, on this line is an intersection point. So every point on this line is my solution. Okay, so these are the two special cases that you're going to see. And if you look back at the last one, here in the parallel line case, you had 0, 0, and then a non-zero number on the right side of the vertical bar, and that gave you no solution for an answer. In the coinciding lines case, you get 0, 0, and then also a 0 on the right side of the bar, and in that example, your solution is the equation of the line. So if you get zeros across the bottom, you need to see if you get a 0 on the right side or a non-zero on the right side to determine whether it's no solution or the whole line. Okay, so those are your two special cases to be on the lookout for. Look for those 0 rows. Okay, the last examples that we're going to work on here are going to be 3 by 3 systems. We can still use matrices for these, but they're just going to be a little bit longer and a little bit more tedious to do. And we're going to do them just like we did the last examples. We're going to start by translating our equations into rows. So in this example, we're going to have 3 rows. The top row is 2, 4, -3, -18. The middle row is 3, 1, -1, -5. And the bottom row is 1, -2, 4, and 14. Now, because this is a bigger system, we have a more involved goal in mind. We still want to get those 1s along the diagonal, but this time there's going to be 3 1s along the diagonal. We need to get zeros below that diagonal and numbers above and to the right of that vertical line. So this is what the reduced row echelon form is going to need to look like. In terms of how to proceed, you usually want to get that upper left one first, and then you want to get these 2 zeros below it second and third. Okay, and it doesn't matter which one you get first, but you want to get this whole first column to be 1, 0, 0 first before you start working on the other 2 1s or this 0 down here. And that's key. If you don't get this first column, then you're going to start going in circles and you're never going to get to your final goal. So get your 1 first and then get the 2 zeros below it. Once you have that, then you're going to try to get this 1 in the middle next so that you can get the 0 down below it. And very last thing to do is get that last one in the diagonal. So that's kind of the order in which you want to try to approach these matrices. So if I look at my original matrix, we're trying to get a 1 in this upper left corner. Right now there's a 2 there, but we see a 1 down here, which is good to use. All I would have to do is swap row 1 and row 3, and then I'll get that 1 in that upper left corner like I want. So let's go ahead and do that. So the top row will become 1, -2, 4, 14. I'll keep the middle row the way it is, 3, 1, -1, -5. And now the new bottom row is 2, 4, -3, -18. Once you get your 1, you will always be able to get your zeros. So the way we get zeros is we look at the number we're trying to eliminate. Let's say we want to eliminate 3. Then I need to multiply row 1 times -3 and add that result to row 2 so that the 3 and the -3 will cancel out. This is that 2-step process. So first we're going to multiply. -3 times 1 would be -3. -3 times -2 is 6. Oops, sorry about that. My pen is acting funny here. Let's get rid of all that mess. Alright, so -3 times -2 is +6. -3 times 4 is -12. And -3 times 14 is -42. Now we're going to take those little red numbers and we're going to add them to that second row so that we can try to get our 0. So in your matrix, you want to keep the row that had the 1 alone. So we're not going to change that. The top row should stay 1, -2, 4, 14. The answer that we get when we add our -3 plus our 3, that's a 0. That's going to go in my middle row. 6 plus 1 is 7. -12 plus -1 is -13. And -42 plus -5 is -47. We haven't even touched this third row yet, so it's going to stay the same. So now we have our 1, we have one of our zeros. We need to get this third 0 down, or the second 0 down here in the third row, and then we'll have that first column all finished off. To get that to be a 0, we're going to do exactly the same process we just did, but this time we want to eliminate a 2. So we're going to multiply our row 1 times -2 and add that to row 3. So first let's do our multiplication. Negative 2 times 1 is negative 2. Negative 2 times negative 2 is positive 4. Negative 2 times 4 is negative 8. And negative 2 times 14 is negative 28. We're going to add that answer to row 3. So we keep row 1 the same. We keep row 2 the same. And we put our answer in row 3. Negative 2 plus 2 is 0. 4 plus 4 is 8. Negative 8 plus negative 3 is negative 11. And negative 28 plus negative 18 is going to be, let's see, 16, carry 1, negative 46. So there's my new matrix. I have a 1, a 0, and a 0. So that whole first column is now done. Once you get that first column done, the next thing you want to get is the 1 in the middle. And to do that, you're going to be looking at these two numbers only to get a 1. So somehow using those two numbers, I need to get a 1. And if I have a 7 and an 8, that's not too hard to do because I can just subtract 8 minus 7 and that'll give me a positive 1. So what we're going to do here is take row 3 minus row 2. I'm going to do row 3 minus row 2 so that I get a positive 1. So let's write out what we get. Leave the top row alone. We're not going to use that row for the rest of the problem. It's now done. Only row 2 and row 3 are going to change. So when I do my subtraction, we're going to do the bottom number minus the top number. 0 minus 0 is going to stay 0. 8 minus 7 becomes 1. Negative 11 minus 13, be careful here, negative 11 minus negative 13, you get a double negative there, so negative 11 plus 13 gives me 2, positive 2. And then we want to do the bottom number minus the top number, so negative 46 minus negative 47 gives us another double negative, so negative 46 plus 47 is positive 1. So I put my answer in row 2 because that's where I wanted that 1 to be. Now I can either keep row 2 or row 3, it doesn't matter. I'm going to go ahead and just keep row 3 where it is. So we have our 1, 0, 0, we have our middle 1. Now what we want to get next is the 0 below that 1. So I want to change this 8 to a 0. And if you have a 1, you can always get the 0 below it by multiplying by the opposite and adding it to the number you're trying to get rid of. So if I want to get rid of 8, then I'm going to take row 2 times negative 8 and add that to row 3. So let's do our multiplication first. 0 times negative 8 stays 0. Negative 8 times 1 is negative 8. Negative 8 times 2 is negative 16. Negative 8 times 1 is negative 8. And we're going to add that answer to row 3. So we're keeping row 1 the same. We're not changing that for the rest of the problem. We're going to keep row 2 the same because it has the 0 and the 1 that I want. And the answer is going to go in row 3. 0 plus 0 stays 0. Negative 8 plus 8 is 0. Negative 16 plus negative 11 is negative 27, and negative 8 plus negative 46 is negative 54. So we have our 1, 0, 0, our next 1 and 0. The last thing we need to get is this last 1. You can always get that very last 1 by dividing, always. So all I have to do here is take row 3 and divide by this number I'm trying to get rid of. So I'm going to divide through by negative 27. So that's going to give me 1, negative 2, 4, 14, 0, 1, 2, 1, and I'm only changing row 3. So we get 0, 0, negative 27 divided by negative 27 is 1, and negative 54 divided by negative 27 is positive 2. We get a nice whole number there. That's what you want to see to kind of know that you're doing it right. If you ended up with a fraction, then that's a clue that your arithmetic is off somewhere. Okay, that's a lot of work to get it into this reduced row echelon form, but we have it now. We have all our 1s along the diagonal. We have all our 0s down below the diagonal. So we're ready to get our final solution. Column 1 is x, column 2 is y, column 3 is z. So right here, what we're getting is that z must be 2. So there's part of our answer. So then how do we find y and x? You back up one row at a time. So if we back up one row and translate this back, this turns into y plus 2z has to equal 1, but we know that z is 2, so let's substitute that in. We get y plus 4 equals 1, and if we subtract 4, that tells me that y is negative 3. So now I know z and y. So then I'm going to back up one more row, and that's going to tell me x. So let's translate this. We get 1x minus 2y's plus 4z's has to equal 14. And if we substitute in, y is negative 3 and z is 2. So we get x plus 6 plus 8 equals 14. That's x plus 14 equals 14, and that implies that x must be 0. So our final solution is going to be 0 for x, negative 3 for y, and 2 for z. As you can see, these are very long problems to do. Whether you do it with a matrix or whether you do it by elimination, it's still a lot of work. Remember that matrices are just an alternative to the elimination method. It's just a different way of getting a solution. So it's just an alternative method. Okay, let's try another one of those 3x3s. These are kind of tough to do. So we're going to start by translating our equations, and I'm going to use a little foresight here. If you look at your three equations, remember our goal is to get 1s along the diagonal, 0s below, and numbers above and to the right. So if we want to have a 1 in that upper left corner, then we want to put as our first row one of the equations that has a coefficient of 1. If you look at this middle equation, the coefficient on x there is a positive 1. So let's just go ahead and put that one in the top right away, and it just saves you one step of writing. So if I put this equation first, I'd have 1, 1, negative 2, negative 8. And then for my second row, I'll just use the top one here, 3, negative 2, 1, and 9. And the bottom equation is negative 1, negative 2, 3, and 13. So we already have the 1 in that upper left corner. I should be able to get these two numbers below into zeros. So let's work on that 3 first. In order to get rid of that 3 and make it a 0, we're just going to take row 1 times minus 3 and add that to row 2. So if we do the multiplication first, 1 times negative 3 is negative 3, another negative 3, negative 2 times negative 3 is 6, and negative 8 times negative 3 is positive 24. We're going to add that to row 2. So my new matrix, I'm going to leave the top row alone because it has the 1 that I want to keep. I'm going to put my answer in row 2. So negative 3 plus 3 is 0, negative 3 plus negative 2 is negative 5, 6 plus 1 is 7, and 24 plus 9 is 33. Okay, leaving the bottom row the same, we get negative 1, negative 2, 3, and 13. So now we have a 1 and a 0. Now we want to get a 0 in this bottom position, which we can do by just adding row 1 and row 2 right away because they are already the same number and opposites. So we're going to keep row 1 the same. We're going to keep row 2 the same. And row 3 is going to be my answer when I add. So 1 plus negative 1 is 0. 1 plus negative 2 is negative 1. Negative 2 plus 3 is positive 1. And negative 8 plus 13 is 5. So we have our 1, 0, 0. Next thing we want to get is this middle 1. So you're going to get that from these two numbers right here. And I already have a negative 1, so if I multiply through by a negative 1 times row 3, that's just going to change all of these signs. So let's go ahead and do that. Keeping the top row the same, the middle row the same, and multiplying through by negative 1, I just get 0, 1, minus 1, minus 5. And now I have a 1, I just have it in the wrong spot. So all I'm going to have to do now is swap row 2 and row 3, and that will get me the 1 in the position I'm looking for. So this becomes 1, 1, negative 2, negative 8, 0, 1, minus 1, minus 5, and 0, negative 5, 7, 33. So I just swapped these two rows. So now I have the second 1 in that diagonal. Once I have a 1, I can always get the zeros below it, because all I have to do is take that row, row 2 in this case, times the opposite of the number I'm trying to get rid of. So I'm going to need to multiply by positive 5 and add that to row 3. So let's multiply first. 0 times 5 stays 0, 1 times 5 is 5, negative 1 times 5 is negative 5, and negative 5 times 5 is negative 25. And we're going to add that to row 3. So my answer becomes 1, 1, negative 2, negative 8, leaving row 1 the same, leaving row 2 the same, because it has the zeros and the ones that I want to keep, and putting the answer in row 3. 0 plus 0 is 0, 5 plus negative 5 is 0, negative 5 plus 7 is 2, and negative 25 plus 33 is 8. So we have our 1, 0, 0, we have our 1, 0. The last thing we need to do is change this 2 into a 1, and remember you can always do that by dividing, so we're just going to take row 3 and divide by 2. So our final matrix looks like 1, 1, negative 2, negative 8, 0, 1, minus 1, negative 5, 0, 0, 1, 4. So we're ready to get our solutions because we have all our 1s and all our zeros. So right here, we know that z must be 4. Back up one row, remember x, y's, and z's, so this becomes y minus z equals negative 5. We substitute in 4 for z and add 4 to both sides. That tells me that y equals negative 1. Negative 5 plus 4 is negative 1. So now we know y and z. So we back up one more row. Translating this, we get x plus y minus 2z equals negative 8. And let's substitute in. Y is minus 1. Z is 4. So we get x minus 1 minus 8 equals negative 8, or x minus 9 equals negative 8. And if I add 9 to both sides, negative 8 plus 9 gives me x is 1. So my solution is 1 for x, negative 1 for y, 4 for z. Okay? Alright, a lot of work for these 3x3 matrices, but it's also going to be a lot of work if you did it by the elimination method as well. So there's really no getting around how you solve these and trying to take shortcuts. Just going to have to keep plugging away until you get down to a simplified system. Alright, our very last example here. Okay, this is another 3x3 system. And again, using a little shortcut here, notice that the coefficient of x on that last equation is a 1 already. So let's put that bottom equation as our top row. So this would become 1, 1, 2, 65. And then I'm just going to recopy the top equation for my middle row and the middle equation for my bottom row. Okay, so now we're ready to go ahead and try to get to that reduced row echelon form. Ones along the diagonal, zeros below, numbers above and to the right. And I already have the 1. I want to get some zeros. Now there's a couple ways to do this. We can just go ahead and do our standard, multiply the top row by -2 and add it to row 2. But there is, one thing you could notice here. You could notice that 2 and 2 right here, if I just subtract row 2 minus row 3, that will also get me 0. So let's try that just as an alternative here. There's usually more than one way to get your solution. So I'm going to leave row 1 alone for now. And if I do row 2 minus row 3, let's write that answer in row 2. So 2 minus 2 is 0. 3 minus 1 is 2. 2 minus 3 is -1. And 100 minus 100 is going to be 0. Now you have your choice of which row you want to keep. You could either keep row 2 or row 3. I'll just keep row 3 since I'm writing it in row 3. So that is one way of getting a 0. Okay? To get the last 0 down here, I'm going to have to use that other method we've been using throughout the notes today. If we want to get rid of 2, then we're going to multiply row 1 times the opposite, -2, and add that to row 3. We're going to do the multiplication first. So -2 times 1 is -2. -2 times 1 is -2. -2 times 2 is -4. And 65 times -2 is -130. And we're going to take those little red numbers and add them to row 3. So our new matrix, leave the top row the same because it has the 1 that we want to keep. Leave the middle row the same because it has the 0 that we want to keep. And now if we add down, -2 plus 2 is 0. -2 plus 1 is -1. -4 plus 3 is -1. And -130 plus 100 is -30. So we got our 1, 0, 0. Okay, now what do we need to do? We got our first column done. Now we need to get this 1 in the middle. So you're going to get that from these two numbers right here. And we get a little bit lucky here because we have a -1. So I can just take -1 times row 3, and that will change all of these minus signs to pluses. And now that I have a +1, all I have to do is swap row 2 and row 3, and that will put the 1 in the position that I want it in. So we're going to keep the top row the same, that's not going to change. But now when I swap row 2 and row 3, then this bottom row becomes 0, 1, 1, 30, and the new bottom row becomes this second row, 0, 2, -1, 0. So I just got that 1 in the position that I wanted it in. So we have our 1, 0, 0, we have our 1. The next thing to get is to make this 2 turn into a 0. So if we have a 1 above it, we can always make that happen. We're going to take row 2 times the opposite of the number we're trying to get rid of. We want to get rid of 2, so I need to multiply by -2 and add that to row 3. If we multiply first, 0 times -2 stays 0. 1 times -2 is -2. 1 times -2 is -2 as well. And 30 times -2 is -60. And we're going to add those numbers to row 3. So our new matrix is 1, 1, 2, 65. Keep the middle row the way it was originally, 0, 1, 1, 30. And the new bottom row becomes 0 plus 0, so that's 0. -2 plus 2 is 0. -2 plus -1 is -3. and negative 60 plus 0 is negative 60. So we have our 1, 0, 0, our 1, 0. The last thing we got to do is change that negative 3 into a 1. And we can always do that by dividing. So we're going to take row 3 divided by negative 3. So final matrix, 1, 1, 2, 65. 0, 1, 1, 30. And then finally dividing through by negative 3 all the way across the bottom row, we get 0, 0. Negative 3 divided by negative 3 is 1, and negative 60 divided by negative 3 is 20. So we have all our 1s, all our 0s, we're ready to get our solution. So right here, we have z. z is 20. Back up one row. If I translate this, we get 1y plus 1z equals 30. If I substitute in 20 for z and subtract 20, we get y is 10. And then I'm going to back up one more row and translate. That gives me x plus y plus 2z equals 65. And if we substitute in, y was 10, z was 20. So x plus 10 plus 40 equals 65. So x plus 50 equals 65. And if I subtract 50, that gives me x is 15. So final answer, 15 for x, 10 for y, and 20 for z. Okay, let's take a look at a few more examples of 3x3 systems. These matrices are tricky, and I want to give you a few more pointers on some tricks you can use to help make them go a little bit smoother. So let's take a look at this example. We want a 1 in that upper left corner. So to help us save some time with writing, let's notice that this middle equation has a coefficient of 1 for x. So I'm going to go ahead and put that at the top. So 1, 1, 2, 19. Let's go ahead and put row 3 in the middle. So 1, 3, 2, 25. And the top row, 3, 1, 2, 31. So we already have that 1 in the upper left corner, which means we want to use it to get the zeros below it. So if I wanted to make this 1 be a 0 and I already have a 1 above it, then one really easy way to do that is to just subtract, since the numbers are already the same. So I'm just going to do row 1 minus row 2. So row 1 is not going to change, 1, 1, 2, 19. And if I do row 1 minus row 2, that's the top number minus the bottom number. So 1 minus 1 is 0, 1 minus 3 is negative 2, 2 minus 2 is 0, and 19 minus 25 is negative 6. I haven't touched row 3 yet, so it's going to stay the same. So now I have my first 0. I want to get another 0 below it, so I want to turn this 3 into a 0. And you should always be able to do that by using the 1 up above it. So we're just going to multiply this row 1 by the opposite of the number we're trying to get rid of. So if I want to get rid of 3, then I need to multiply by negative 3, and I'm going to add that result to row 3. So let's multiply this entire top row by negative 3. So I'm going to get negative 3, negative 3, negative 6, and 19 times negative 3 is negative 57. Then we're going to add those numbers down to row 3. So the top row stays unchanged. We're keeping the original row with the original 1. The middle row we're not using right now, so it's going to stay the same. And the new row 3, negative 3 plus 3 is 0. Negative 3 plus 1 is negative 2. Negative 6 plus 2 is negative 4. And negative 57 plus 31 is negative 26. So now that first column is done. We have our 1, 0, 0. So the hard part, usually for 3x3 matrices, is these two numbers right here. Trying to get that middle number to be a 1 and a 0 below it. Right now, these two numbers are exactly the same, so there's no easy way to get them to be just a 1. We can't add them together, we can't subtract them. Things like that aren't going to work to try to get them to be a 1. So here's one trick that I like to use, and this happens quite often in these problems, so please look for that. What you're going to notice is that all of the numbers in row 2, they're all divisible by -2. You can also notice that in row 3 as well, since all the numbers are even. So one of the things I like to do is if I see that a row is divisible by a common factor, then I always divide through by it. So I'm going to divide row 2 by -2. I'm also going to divide row 3 by -2. So that's going to give me 1, 1, 2, 19. And the second row becomes 0, 1, 0, 3. And the third row becomes 0, 1, 2, 13. Now dividing through by a common factor like that always gives you a row with smaller numbers that are hopefully much easier to work with. And the added benefit on this problem is, notice what I have right here in the middle. Now I have that 1 that I was looking for. So by dividing through by common factors, you can sometimes get that 1 that you're looking for. Now that I have a 1 in the middle, I want to get a 0 below it. So an easy way to do that, since they're both 1s, is just to subtract row 2 minus row 3. So we're not changing row 1 at all. We're not going to change row 2 at all because it has the 1 that I wanted. And the new row 3, when I do second row minus third row, 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 2 is -2, and 3 minus 13 is -10. So column 1 is done, column 2 is done. All I have to do now is change this -2 into a 1, and you should always be able to do that by dividing. Here I'm going to divide through by that -2. So my final matrix is 1, 1, 2, 19, 0, 1, 0, 3, and 0, 0, 1, 5. So I have that nice reduced row echelon form that I was looking for. So now we should be able to get our final solution. This bottom row tells me that z is 5. We get a little lucky here in the middle row because I have a 0 in the first and third spots, so there's no x's and y's, no x's and z's, so this just tells me that y is 3. I don't have to do any solving. And if I go all the way back to the top, this tells me that x plus y plus 2z equals 19. So substituting in, I get x plus 3 plus 2 times 5 equals 19. So x plus 3 plus 10 is 19. X plus 13 equals 19. So x is 6. So my final solution is 6, 3, 5. Okay, let's try another one. Now on this one, if you look at your coefficients of x's, notice none of them are exactly equal to 1, but that middle one is at least a -1. So I'm going to put that at the top. So let's put -1, 3, 4, -6, and then I'll put the top equation 1 into the second row, and 5, -5, 6, 45 on the bottom. So I don't have exactly a 1 in the upper left, but it's pretty close. All I have to do is get rid of that negative. So let's go ahead and multiply through by a -1. So this becomes 1, -3, -4, +6, and the other two rows stay the same. Alright, I have my 1. Now I want to get my zeros below it. So all I'm going to do now is get rid of that 3 by multiplying row 1 by -3 and adding that to row 2. So this becomes -3, +9, +12, -18, and we're going to add down. So the first row stays put. The new second row becomes -3 plus 3 is 0, 9 plus -2 is 7, 12 plus 2 is 14, Negative 18 plus 18 is 0, and I'm not using row 3 yet. Okay, let's go ahead and change that 5 into a 0, doing exactly the same thing, but this time we're going to multiply row 1 by minus 5 and add that to row 3. So this would be minus 5, 15, 20, and negative 30, and we're going to add down. So the top row stays put, the middle row stays put for now, and the new third row is negative 5 plus 5, which is 0, 15 plus negative 5 is 10, 20 plus 6 is 26, and negative 30 plus 45 is 15. Alright, so that first column is done. Now what we want to focus on is right here. We want to get that to be a 1 and a 0. And if I look at 10 and 7, they have a difference of 3, so that's not a good way to get a 1. But if I look for that same trick that we did on the last example, notice that this second row has a 7 and a 14 and a couple of zeros. So that means that entire row is divisible by 7. So let's go ahead and divide by 7. And that will magically give me that 1 that I'm looking for in the middle. So equation 1 stays the same, and our new middle row is 0, 1, 2, 0. The third row I'm going to leave the same. And now I have that 1, so in order to get a 0 below it, I can just use that 1 in row 2 and multiply by the opposite of the number I'm trying to get rid of, so in this case a negative 10, and I'm going to add that to row 3. So when I multiply through by negative 10, this stays 0, this is negative 10, negative 20, and this stays 0. And I'm going to add down. So row 1 stays put, row 2 stays put, and the new row 3 is 0, negative 10 plus 10 is 0, negative 20 plus 26 is 6, and 0 plus 15 stays 15. So row 1 is done, row 2 is done. Last but not least, we want to change this 6 into a 1, which we should always be able to do by dividing. Notice on this one, however, when I do divide by 6, 6 does not go into 15 evenly. So we are going to get a little bit of a fraction here. 15 divided by 6, when I reduce that, is 5 halves. So we do get a fraction, and I'll warn you that probably most instructors would never give you a problem on a test or a quiz that will have fractions as an answer, but occasionally in your textbook or in a homework problem you might run across one. You never, ever, ever want to involve fractions in your matrices until the very last possible step, the very last moment. If you have a bunch of fractions up here, it's just going to be a great big mess and a huge headache for you. So try to avoid fractions at all cost until the very, very last step. So this tells me that z is 5 halves. Let's back up one step. We get 1y plus 2z's equals 0. Since z is 5 halves, if I substitute that in, notice the 2's are going to cancel, so we get y plus 5 equals 0, or y equals negative 5. And then if I back up all the way to the beginning, I get x minus 3y minus 4z equals 6. So x minus 3 times negative 5 minus 4 times 5 halves equals 6. So x plus 15. 2 goes into 4 twice, and 2 times 5 is 10. So that means 4 times 5 halves is just 10. 15 minus 10 is 5, and if we subtract 5, that's going to give me x is 1. So my solution is going to be 1, comma negative 5, comma 5 halves. Okay, so our last problem here looks like this. And we have no ones in that X position, unfortunately. So I don't see any ones, so I'm just going to go ahead and recopy these rows in exactly the order that they're given to me. So 3, -6, 3, -9, 2, 1, 3, 1, -3, 1, -2, and -4. So on this one, we want to get a 1 in that upper left column. And on this particular example, there's multiple ways to do that. So here's some things that I would look for. First of all, that trick that we've been using quite often now, if you see an entire row that is divisible by a common factor, go ahead and divide through by that so that your numbers become smaller and more manageable and easier to work with. Hopefully you notice in that very first equation, that entire row is divisible by 3. So if I were to divide by 3, I magically get that 1 that I'm looking for. So 1, -2, 1, -3, and everything else will stay the same. None of the other 2 rows are divisible by a common factor. So that's one really simple way to get that 1. If that didn't happen, if that wasn't possible, there are other ways to get a 1. Notice that you have a 3 and a 2, so one way to get a 1 would be to subtract row 1 minus row 2, or you could have used row 3 and row 2 and then taken its opposite. So there's lots of possibilities, and just because I'm showing you one way doesn't mean that's the only way to correctly solve the problem. That's probably one of the hardest parts about matrices, is that there's usually multiple ways to do the problem, so it's hard to kind of come up with a standard technique that works every single time. Alright, we have our 1, now we should be able to get our zeros. So I'm just going to take this row 1, I want to get rid of 2, so I'm going to multiply by -2 and add that to row 2. So this would be -2, +4, -2, +6. So if I add that down, we are going to get the following matrix. So here's what we have. We've got 1, -2, 1, -3. That's not going to change. In our second row, we now have a 0, 5, 1, and 7. And I haven't done row 3 yet. Let's do that again to get rid of the -3 in the bottom. So I'm going to multiply by +3 and add that result to row 3. So this is 3, -6, 3, and -9, and I'm going to add that down. So row 1 stays the same, row 2 stays the same, and the new row 3, 3 plus -3 is 0, -6 plus 1 is -5, 3 plus -2 is 1, and -9 plus -4 is -13. Alright, so I have that first column done. I want to try and get a 1 and a 0 in the middle, so we're going to focus on these 2 numbers right here. Neither one of them is a 1, and they're almost identical, but they're opposites. So if you're looking at a 5 and a -5, just adding them together would very easily give you a 0, but it's not going to give you a 1. So if we wanted to try to get that 1 first, there's really no good way to manipulate 5 and -5 to make that happen. So one of the other things again that you want to check for is there a number that divides through that entire row 2 or that row 3? And in this case, unfortunately, there isn't a common factor that goes into everything in row 2 or everything in row 3. So that little trick doesn't work. So all of my options are kind of used up here. We don't have a good, easy way to get a 1. So sometimes what I recommend is if it's really difficult to get a 1 and you can't figure out how to do it, then go for that 0 first. And in this case, you have a 5 and a -5. So a really easy way to get a 0 is just to add together row 2 plus row 3. So let's go ahead and do that. Row 1 stays the same. I'll leave row 2 the way it is for now, and when I add row 2 and row 3 together, 0 plus 0 stays 0, 5 plus negative 5 is 0, 1 plus 1 is 2, and 7 plus negative 13 is negative 6. So unless I wanted to divide through by 5, there's no good way to get a 1 right in the middle there. And I wouldn't really want to divide by 5 because that's going to give me fractions over here and here. So sometimes you have to kind of give up a little bit on that perfect reduced row echelon form. That's really just a suggestion for the optimal or ultimate way to make solving for x, y, and z as easy as possible. But if you can't get all those 1s and all those 0s, just try to get your matrix as close to that as you possibly can. So I've got most of my 0s, and I wasn't able to get the 1 in the middle, but I can get the 1 at the very end here by just dividing by 2. So let's finish this off and divide by 2, and here's my final matrix. It's not perfect because I have that 5 in the middle, but it's pretty close to that nice reduced row echelon form. Okay, so now all we have to do, even though we didn't get it perfectly in the right form, we got it pretty close enough that we can now finish the problem fairly easily. This bottom row, because I was able to get that 1, tells me z right away. Z is negative 3. If I back up one step, I get 5y plus z equals 7. So 5y minus 3 equals 7. Add 3. 5y equals 10. So y equals 2. And then if I go all the way to the top, x minus 2y plus z equals negative 3. So if I substitute in 2 for y and negative 3 for z, we get x minus 4 minus 3 equals negative 3. X minus 7 equals negative 3. So x equals positive 4. So my final solution is 4, 2, negative 3. So remember some of those tricks, trying to divide through by a common factor. If that's not possible, see if there's a way to add or subtract your 2 rows together to get a number that's equal to 1, or if that's not possible, then see if you can get that 0 first. Alright, good luck. This concludes our lecture on using matrices to solve systems of equations.